In a remark from Professor Carlos Frank of Durham University, "I've spent my entire life building a certain view of the world, and now that idea is being questioned. I welcome it because it is how we advance in science." James Webb is overturning almost everything in cosmology that has been accepted as true for the past century. A new ultra-deep image confirms that we have made mistakes in astronomy. The telescope that was supposed to reveal to us the first stars of the universe is destroying the prior worldview and may usher in a new science. Not all researchers are scared by the new information. Many scientists welcome the advancements because it has long been evident that something was amiss with our previous hypothesis. The inconsistencies in measuring the universe's expanding pace should have woken academics up years ago. Instead of properly reading the signals, they stuck to outdated notions. The cosmic microwave background radiation, CMBR, is thought to be the oldest in the universe. The CMBR was formed approximately 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for electrons and protons to form stable hydrogen atoms. Researchers refer to this transformation as reionization, and it made the universe permeable to light. The CMBR was discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were developing a new type of antenna. They saw a steady noise coming from all directions in the sky. This discovery was long regarded as one of the most compelling pieces of evidence supporting the Big Bang theory. Penzias and Wilson shared the Nobel Prize and made history in astrophysics. The CMB most likely provides a glimpse of the young universe. Tiny temperature changes provide significant information about the circumstances in the universe shortly after the Big Bang. Scientists used the CMB to measure the universe's expansion rate, among other things. Edwin Hubble, an astronomer, had already made this computation in the late 1920s. Hubble discovered that distant galaxies move away from us in all directions with speed proportional to distance. Today we refer to these measurements as the Hubble rule or the Hubble constant. Of course, Hubble did not yet have the advanced measurement techniques that were employed decades later when the CMB was discovered. Researchers recalculated the rate, and the new figure is substantially lower than Hubble's original estimate. Later, scientists recalculated the rate using Type Ia supernovae as the standard candles. Astronomers had access to such stable light that it could be utilized as a dependable measuring point. The discrepancy in determining the universe's expansion rate has existed since the 1990s. Since then, researchers have known, or rather suspected, that something was wrong with the assessment of the CMBR, the measuring methods, or the concept of cosmic expansion. The S8 tension or Hubble tension refers to the difference between the various measured measurements of the universe's expansion rate. This has far-reaching repercussions beyond a simple measurement difference. The many discoveries reveal profound insights into how we have previously understood the universe. For a long time, scientists were at a loss. Since its inception, the James Webb Space Telescope has provided scientists with some unexpected results, which may now shed light on the conundrum of the universe's expansion rate. Galaxies so old and mature that their origin must have occurred before the Big Bang are completely in traditional science and astrophysics. There is no longer talk of measurement inconsistencies. Instead, academics are discussing the most serious problem in contemporary astronomy. Not only could the universe's expansion pace be erroneous, but the entire concept of expansion or the Big Bang is being tested. Webb's photos reveal evidence of a world that is vastly different from what we have long believed. The tension served as a first warning, and all researchers who continue to believe in outdated theories now face a challenge. Do we actually know nothing about the universe? Many scientists are now standing on the rubble of their life's work, staring into space in despair and unable to comprehend what they are seeing. Given the current scientific dilemma, we must ask ourselves, what do we truly know about the universe? To address this question, we must first grasp how science works. Theoretical scientists employ a complicated network of mathematical models, empirical data, and deductive reasoning to reach findings ranging from general to specific. Their expertise is based on a combination of observed events, experimental data, and extensive theoretical analysis. The name theory alone indicates that these are creations and ideas, not reality. We only have practical knowledge in the form of images from telescopes, sound waves and radiation captured by radio telescopes, and the most recent data from neutrino measuring systems or gravitational wave detectors. With the James Webb Space Telescope, we now have equipment at our disposal that allows us to break down the earliest light into individual frequencies and analyze it in ways that were previously impossible. Webb can show us which elements were prevalent in galaxies over 13 billion years ago, how much mass was contained, and how many stars. This indicates the telescope can rebuild a galaxy's form and direction of travel. However, Webb may have flaws in some of his photos. Because of massive accretion disks, the telescope cannot tell us whether we are looking at galaxies or black holes that shine as brilliantly as galaxies. We must confront the fact that our science has long accepted too many possible outcomes as realities while ignoring alternative explanations. Research has long been certain that it is correct. The most recent findings from the James Webb Telescope provide vital indications for replacing ideas with new truths, as has happened dozens of times in science. Scientists are currently awaiting new results. The current discoveries are far too bizarre, and it appears impossible for many researchers to come up with fresh interpretations. Right now, the new discoveries are challenging the basis of modern physics, which scares many scientists. Today's physics courses are mostly based on Isaac Newton's discoveries in the 17th century. For centuries, his principles of motion and gravity served as the cornerstone for our physical understanding of the real world, including the universe. Newton's rules explained the movements of objects under normal conditions and worked well on Earth. In space, however, his concepts needed to be expanded, which Albert Einstein substantially accomplished at the turn of the 20th century. His special theory of relativity, published in 1905, transformed our view of space and time. Einstein demonstrated that space and time are related to one another and depend on the movement of the observer. The general theory of relativity, published in 1915, expanded on the concept by providing mathematical evidence of gravitational phenomena based on the curvature of spacetime caused by masses such as stars or galaxies. Einstein's theories and concepts were generally cohesive, yet he did approach his limits. Throughout his life, the researcher was aware that his theories would never be sufficient to describe the entire cosmos. He hoped to discover the world formula, but he did not succeed. Interestingly, no other researcher has succeeded to this day. Where's the mistake? Wouldn't it be interesting to know where the mistake is? Michio Kaku, a prominent astronomer from the United States, stated in an interview that the person who answers this challenge will undoubtedly win the Nobel Prize. Let us investigate what facts scientists may have ignored, where they may have misconstrued events, and whether our telescopes are at fault. Dark matter and dark energy are among the most likely sources of the cosmic catastrophe. Our current theories of the cosmos incorporate the idea that dark matter and dark energy together account for around 95% of the universe. However, neither has ever been directly witnessed, and so their true existence has never been established. Either they do not exist at all, and we must explain the universe's expansion and galaxy dynamics separately, or both have qualities that we do not yet understand. One theory now being discussed is that the physical properties of the two dark components have evolved over time, which could imply that we are dealing with some form of intelligence. The next thing to be tested is gravity. This force, which presumably causes attraction or curvature in spacetime due to mass, has yet to be demonstrated. Einstein is significantly responsible for the concept of spacetime curvature, which has been repeatedly proven correct. However, we cannot rule out the possibility that gravity has entirely different qualities than previously thought, or that the gravitational force between objects is caused by a different mechanism. Several values known as cosmic constants have been established in modern cosmology and astrophysics over the years. These values are largely trustworthy because they rarely change. Calculations have revealed that slight fluctuations in these purported constants introduce fresh momentum into the universe, allowing us to explain a variety of events without the existence of dark energy. It is also possible that our interpretations of the redshift of light are erroneous and that we have been measuring incorrect distances within the universe and determining galaxies' ages for decades. Perhaps our beliefs about the universe's original state were likewise erroneous. We may have misread the cosmic microwave background radiation. It's also possible that the universe cannot be traced back to a single origin point. This would imply that the Big Bang theory is erroneous. Although we have sophisticated technology, we cannot rule out slight errors in the Webb telescope or other observational instruments. In the midst of the crisis, engineers and scientists agree that errors in instrumentation, data processing, and interpretation are always possible. The field of cosmology stands at a crossroads today, where the foundations laid over centuries are being challenged by new observations and data from advanced instruments like the James Webb Space Telescope, JWST. These challenges not only question established theories but also open up avenues for entirely new understandings of the universe and its origin. One of the central pillars of modern cosmology is the concept of the Big Bang, which proposes that the universe originated from an infinitely dense point and has been expanding ever since. This theory has been supported by various lines of evidence, including the cosmic microwave background radiation, CMB, the Hubble constant measurements, and the distribution of galaxies across the cosmos. The discovery of the CMB in 1964 was a watershed moment in cosmology. It provided strong evidence for the Big Bang theory by showing a uniform glow of radiation across the sky, which is believed to be the afterglow of the hot, dense early universe when it first became transparent to light. This relic radiation has since been studied extensively to understand the composition, age, and geometry of the universe. However, recent observations and measurements, particularly from the JWST, have introduced significant challenges to this established framework. The JWST, with its unprecedented sensitivity and resolution, has started to unveil galaxies and phenomena that defy conventional explanations. For instance, the discovery of galaxies that appear to be older than expected raises fundamental questions about the timeline of cosmic evolution and the processes leading to the formation of stars and galaxies. Moreover, discrepancies in the measurement of the universe's expansion rate, known as the Hubble tension, persist despite decades of refinement in observational techniques. While the CMB-based measurements suggest a certain rate of expansion, independent measurements using Type Ia supernovae as standard candles yield slightly different results. This discrepancy hints at potential flaws in our understanding of either cosmic distances, the nature of dark energy driving the universe's acceleration, or both. Dark matter and dark energy remain enigmatic components of the universe, comprising the vast majority of its content yet defying direct detection. These mysterious substances are invoked to explain the observed gravitational effects on galaxies and the accelerated expansion of the universe, respectively. However, their precise nature and properties continue to elude scientists, leading to various theoretical and experimental efforts to uncover their identities. In addition to these theoretical challenges, the JWST has provided stunning visual evidence of phenomena that challenge our current understanding of cosmic history. Images of distant galaxies, some of which existed just a few 100 million years after the Big Bang, suggest a complex and rapidly evolving early universe that may require new theoretical frameworks to fully comprehend. The JWST's ability to analyze the spectra of light from these ancient galaxies offers insights into their chemical composition, star formation rates, and even the presence of heavy elements crucial for the formation of planets and life. These observations not only enrich our understanding of galaxy formation but also raise intriguing questions about the conditions under which life could emerge in the universe. Furthermore, the concept of cosmic inflation, which posits a rapid exponential expansion of the universe immediately after the Big Bang, remains a topic of debate and scrutiny. While inflationary models provide an elegant explanation for the observed large-scale structure of the universe and the uniformity of the CMB, alternative theories that do not require inflation are actively pursued to reconcile theoretical discrepancies and observational challenges. Beyond the realm of theoretical physics, the JWST discoveries also have profound implications for our philosophical understanding of the universe. They force us to reconsider fundamental questions about the nature of spacetime and existence itself. If the universe's expansion rate varies across different scales or epochs, as some data suggest, it could imply that our cosmic neighborhood is just a tiny part of a vastly larger and more complex multiverse. Moreover, the JWST observations of distant galaxies and their evolution over billions of years offer a glimpse into our cosmic origins and future. By studying how galaxies form, grow, and interact over cosmic time, astronomers hope to unravel the underlying physical processes that have shaped the universe's structure and diversity. The search for answers to these profound questions requires a combination of theoretical insights, observational precision, and technological innovation. Advanced telescopes like the JWST, with their ability to peer deeper into space and farther back in time than ever before, play a crucial role in this quest for knowledge. In conclusion, while the challenges posed by the JWST and other cutting-edge instruments may unsettle established theories, they also present unprecedented opportunities to expand our understanding of the universe. By embracing these challenges and pursuing rigorous scientific inquiry, astronomers and cosmologists are poised to uncover new truths about the cosmos and our place within it. The journey ahead promises to be both thrilling and transformative as we continue to explore the mysteries of the universe and push the boundaries of human knowledge.